Okay, I want you to close your eyes for a second. We're going to take a little trip.
Uh,
You're back in high school. It's third period. And you walk into that specific room. You know the one. It smells like floor wax and pencil shavings and old paper.
oh, wow. Yeah, I can
Oh.
picture it. I can smell it.
You sit down at that wobbly desk. You look up, and on the board it says, Mr. Jones, physical science.
Everyone had a Mr. Jones, the teacher who was like, the world is solvable. You just need the formula.
Exactly. And today we are going back to Mr. Jones's class. But this time, it's not about passing a test. We have a whole stack of his notes, charts, everything on one topic, change of state.
And we're looking at it with, grown-up eyes.
Right. Because reading through this, I realized Mr. Jones was basically handing us the keys to how the entire physical universe works.
It's true. When you get past the vocabulary list, it's really a story about energy, about how things transform.
And to kick this off, I want to start with a mystery that hooked me right away. The notes call it the gallium phenomenon.
Ah, the metal that melts in your hand.
Yeah.
Classic.
It's so wild. So imagine I hand you a chunk of this stuff, gallium. It's a soft, silvery metal. It looks sturdy,
Like a piece of aluminum or something, yeah.
It's used in semiconductor chips, so it's serious stuff. You can cut it with a knife, but it is definitely a solid object.
Right. At room temperature, it's
Oh, yeah.
sitting there holding its shape.
Yeah.
Like a rock.
But then the instructions say, place it in the palm of your hand, and in just a few minutes, you're not holding a rock anymore.
You're holding a puddle.
It just melts. It feels wrong.
It does. Because we think of melting metal as like a blast furnace thing, not your body heat.
Exactly. And that's the mission today. Why does that happen? And what is actually going on in that tiny, invisible universe of particles when something melts or freezes or boils?
It's so much more than just ice gets wet. It's about motion, connections. It governs everything from your ice cubes to literal lava.
Okay, so let's dive in. First thing Mr. Jones's notes clarify is what a change of state even is.
Right. And the big headline here is that it's a physical change, not a chemical one.
Let's unpack that. What's the practical difference?
Well, think about baking a cake. You mix flour, eggs, sugar. You get a cake. You can't unbake it to get your eggs back.
No, definitely not.
That's a chemical change. The substances became something new, but a physical change. The source uses the water is water rule.
Okay.
An ice cube is H2O. A puddle of water is H2O. The steam from a kettle is H2O. The identity is the same.
So you've just changed its outfit, not its DNA.
That is a perfect way to put it, which leads to this crucial idea, the conservation of matter. The notes are very specific here.
This part kind of blew my mind. It says matter is neither created nor destroyed. The number of particles is exactly the same before and after.
Exactly the same. So if that solid chunk of gallium had, say, a billion atoms,
The liquid puddle also has exactly a billion atoms.
not one more, not one less. You haven't lost any, and you haven't created any. They're just arranged differently.
That's like a Lego castle. If I smash it, I still have the same number of bricks. It just looks like a pile.
Perfect analogy.
Yeah.
The building blocks don't just vanish.
So let's solve the gallium mystery then. If the particles are all there, why does my hand make it melt?
It's not magic, it's energy. Thermal energy, specifically. Your
Yeah.
body's warm, right? About 37 degrees Celsius. The gallium is at room temperature, maybe 20,
And heat likes to move from hot to cold.
always. The universe loves balance. So that warmth flows from your hand into the metal. And when you give particles energy, they start to dance.
Which brings us to the particle dance. We've got three big terms here: kinetic energy, thermal energy, and temperature. I'll be honest, I usually just use them to mean heat.
Most people do. But in Mr. Jones's class, precision matters.
So let's break it down. Kinetic energy, the energy of motion, and the source says every particle is always moving, even in a solid brick.
Even in a solid brick, to your eyes, it looks still. But if you could shrink down to the atomic level,
It's a different story.
totally. In a solid, the particles are locked together by these really strong attractive forces, but they aren't still. They're vibrating in place.
Okay, I was thinking about this. Is it kind of like a packed football stadium? Oh, I like that. Tell me more.
So the solid is the stadium.
Right.
Everyone's in their assigned seat. They can't just wander around, but they're not sitting still. They're bouncing, shivering, they're excited.
That is a perfect visualization. They have kinetic energy, they're moving, but they're confined by the structure, the seats.
Okay, so they're shivering in their seats. Now, I put that gallium in my warm hand. I'm adding thermal energy. What happens to the crowd?
You're pumping energy into the system. So the vibration gets more and more intense. The fans start bouncing harder.
God,
faster.
Until eventually.
Eventually, they're vibrating so violently they break loose from their seats. They overcome those attractive forces.
And that's melting.
That's melting. The particles break out of that fixed pattern. Now they're sliding around each other. The crowd is on the field.
They're still in the stadium, but they can move around.
Exactly. That's why a liquid can flow and take the shape of its container.
And if we keep turning up the heat,
With enough energy, they break away completely. They fly off in all directions. That's a gas. The fans have left the stadium. They're running through the streets.
total freedom, total chaos.
I love that. Now, the notes distinguish between evaporation and boiling.
Yeah.
How are they different?
It's about where it happens. Evaporation is a surface thing. A few particles at the top of a puddle get enough energy from the sun maybe and just pop off into the air.
It's a quiet exit.
Very quiet. But boiling, that's more dramatic. That happens when you're adding energy from the bottom and you're adding it fast.
So you're energizing the particles deep inside the liquid.
Right. And they turn to gas right there, at the bottom of the pot.
And that's what the bubbles are, not air.
Not air. Those bubbles are water vapor. It's gas forming underwater and fighting its way up. It's an internal escape attempt.
Okay, so that makes sense. But this is where the notes got really counterintuitive for me. There's this graph from an experiment called Reggie and the Hot Plate.
Yes. The heating curve. This is a huge aha moment.
So, Reggie puts ice on a hot plate and tracks the temperature. Now, I would guess the line on the graph just goes straight up. You're adding heat, it gets hotter.
That's the logical assumption, right? That's what our brain tells us.
But the graph looks like a staircase. It goes up, then flat, then up, then flat again. What's happened on those flat parts? The hot plate is on, but the thermometer is just stuck.
The thermometer isn't broken. This is the key. Those are the energy plateaus.
But why?
Think back to the stadium. When you're heating the solid ice, the temperature rises because the fans are vibrating faster. Temperature is just a measure of that vibration speed.
Faster vibration, higher temperature. Got it.
But when you hit the melting point, 0 degrees for water, something changes. Suddenly, the energy you're adding stops making the particles vibrate faster.
It's being used for something else.
Exactly. It's being diverted to do the heavy lifting of breaking the bonds. It's the energy cost to get the fans out of those seats.
Oh, so it's construction work.
It is. So until every last crystal of ice is melted, the temperature will not go above 0 degrees.
So if I have a glass with ice and water in it, the water is at 0 degrees.
Exactly 0. Until that last sliver of ice is gone, only then does the temperature of the liquid start to climb again.
That's incredible. It's like a toll booth. You have to pay the energy toll to cross the border from solid to liquid.
That's a great way to think about it. And the same thing happens at the boiling point. The source mentions mercury.
Right, the liquid metal.
You heat it up, it climbs all the way to 357 degrees Celsius. But once it hits 357,
It hits another plateau.
another plateau.
Right.
The temperature stays flat at 357 until all the liquid is turned to gas.
So those flat lines on the graph, that's where the real action is.
That's where the change of state is actually happening. Energy is changing the state, not the temperature.
Okay, so let's flip it around. We've talked about adding energy. What about taking it away, freezing?
Right, reversing the process. You put water in a freezer. The water is warmer than the freezer's air, so energy flows from the water out into the air.
The energy leaves the building.
And as it leaves, the particles slow down, they stop running around, and eventually they move so slowly that those attractive forces grab them again
Pulls them back into their seats.
and locks them into a regular pattern. That's freezing.
But here's where the notes challenged me. When I hear freezing, I think cold, snow, ice.
A very common bias. We confuse the scientific term with the weather report, but in physics, freezing just means a liquid turning into a solid. It doesn't have to feel cold to us.
And the example that really drove this home for me was lava.
Yes, lava is the perfect example.
So it erupts as liquid rock at, 1,200 degrees Celsius, scorching hot liquid.
But as it flows, it hits the cooler air, it loses energy, the particles slow down, and it turns into solid rock.
So technically, that rock is frozen lava.
Scientifically, yes, the lava froze. It just happened to freeze at like 1,000 degrees.
That completely redefines the word. Freezing is just about structure winning over motion.
That's all it is. And here's another weird rule. The freezing point and the melting point are the same temperature.
Wait, say that again?
For water, the freezing point is 0 degrees Celsius. The melting point of ice is also 0 degrees Celsius. It's the same line in the sand.
It just depends on which way you're going.
Exactly. Are you adding energy or taking it away?
Okay, one more transition. The one we see on a hot day with a cold drink, condensation.
gas to liquid.
The sweaty glass. Now, growing up, I honestly thought the glass was, like, leaking.
A lot of people do. But the water's not coming from inside the glass. It's coming from the air.
The air around us.
Yeah, the air is full of invisible water vapor, high-energy gas particles zipping around. Then they hit the cold surface of your glass.
It's like a thermal wall.
It is. They slam into it, transfer a ton of energy to the glass, and slow way, way down.
So slow that they can't stay a gas anymore.
The attractive forces snag them, pull them together, and poof, a liquid droplet forms. It's the reverse of evaporation.
Speaking of the environment, there was one last piece of data in the notes I found fascinating. It was a list of places.
The altitude list.
Yeah. Sea level, Denver, Mount Everest. And it says the boiling point of water is different in all of them. How? I thought water boils at 100 degrees.
Well, this is where pressure comes in. Think about boiling again. Bubbles of gas are trying to push their way out of the liquid,
Okay.
but the atmosphere, all the air above us, is pushing down. It's like a heavy blanket trying to keep the bubbles in.
So at sea level, we've got the standard blanket. Water boils at 100 degrees.
Now go to Denver, the mile-high city. You're higher up, the air is thinner, the blanket is lighter.
So there's less pressure pushing down.
Exactly. The water particles don't have to work as hard to escape. So in Denver, water boils at around 95 degrees.
So boiling water in Denver isn't as hot as boiling water at the beach.
Correct. It's bubbling, but the temperature is lower. On Mount Everest, it's even more extreme. The pressure is so low that water boils at about 70 degrees Celsius.
70 degrees. You could barely make a good cup of tea with that.
You'd really struggle to cook pasta. The water would be bubbling, but it's not hot enough to really cook the noodles. You'd just have lukewarm, soggy pasta.
That is so bizarre. And the Dead Sea is the opposite because it's so low.
Exactly. It's below sea level, so the air pressure is higher. The blanket is thicker. You have to heat the water past 100 degrees to get it to boil there.
So a boiling point isn't a fixed number. It's a relationship with the environment.
Everything we've talked about is a relationship between particles, with energy, with the pressure around us.
So to bring this all home, we started in Mr. Jones's class with a piece of melting metal.
And we realized it wasn't magic, just energy transfer. We saw that matter is conserved, just rearranged.
We zoomed in on the particle dance of vibrating solids, sliding liquids, flying gases.
And we learned about those plateaus on the graph, where the real work of breaking bonds happens.
I mean, why does this stuff matter outside of a science class?
Well, look around. The weather is just a giant cycle of evaporation and condensation. Cooking dinner is all about energy transfer. The computer chip in the device you're listening on was made using these principles with things like gallium.
It's the operating system of the physical world.
It really is. We are surrounded by it.
I want to leave everyone with one final thought from that energy plateau part.
Yeah.
I think it's a great metaphor.
Oh, yeah.
Sometimes, in life, you feel like you're putting in all this energy, doing all the work, but the temperature isn't rising. You don't see the result.
You feel stuck on that flat line.
Exactly. You're on the plateau. But it doesn't mean nothing is happening. It means the energy is being used for something deeper. It's breaking old bonds to change the state of things. The shift is happening, even if you can't measure it yet.
I love that. The invisible work before the real transformation.
So if you feel stuck, just remember Reggie's graph. You might just be building up the energy for a phase change.
Keep putting the energy in.
Thanks for joining us on this trip back to physical science. Keep asking questions, and we'll see you in the next deep dive.